Today I'm going to be talking about what goes on inside the Intel processors that drive many, if not all, of our servers, laptops, and desktops. And I'm going to be sort of going into the details a little bit, so you'll hopefully forgive me if I get into the weeds with some assembly on the screen. But before we go too far on, I have an admission. My talk is called x86 for fun and profit. And my intention originally was to come up with some really strong indicators about how you could optimize your code, how you can profile your code, how understanding the internals of the machine can give you sort of insight into improving your code. But there is so much to cover, and it's so interesting. I just wanted to cover the things that I think are interesting, and hopefully along the way we will pick up some little unusual behavior indicators that we can look for, and some optimization opportunities, but mostly this stuff is just really interesting. And if nothing else, I want you to go away from the end of this talk and have a fresh appreciation for what on earth the Intel and AMD engineers have been able to do behind the x86 facade that they give us, and indeed have some kind of sympathy for those people among us who write compilers and JITs and who are trying to sort of reverse engineer and take advantage of all this fantastic power in front of us. So, Intel are famously tight-lipped on what goes on beyond the x86 instruction set. They have about 7 or 8 feet thick of manuals that you can get that have all manner of detail on the individual opcodes, the bytecodes, how the system management stuff works and all that stuff, but they don't actually tell you how it works inside, mainly because, I believe, they don't want to tip the wink to their competitors, fair enough. They also don't want us to take too much advantage of the internals of a chip as they may change from processor revision to processor revision. But thankfully, there are some people out there who are crazy enough to make it their hobby or pastime to try and reverse engineer as much as possible about what goes on underneath. And this talk wouldn't have been possible without a lot of help from a guy called Agner Fogg, who is at the University of Denmark, I think, and he has made it his life's work to sit down and write test case after test case after test case, and to use all of the internal management counters that are inside the chip and somehow try and derive what is going on under the hood. So a lot of this comes from what he said and some other people who have looked into this and done experiments, and some of my own experiments as well, but mostly I'm standing on the shoulders of these other guys who've come before me. So this is about as much detail as Intel are prepared to give you about what goes on inside this diagram over here. We're going to be talking about the top half and the bottom half. The top half here is the in-order, standard, one instruction after another part of the processor, and the bottom part is where the interesting stuff happens, where everything gets out of order. We're going to be talking about the pipeline, what the branch predictor is, what register renaming is and why it's important, how that out-of-order execution happens, and a little bit on caching. I may have missold that a little bit in the abstract of this talk. I did say that I would be going into caching as well, but again, that's like probably another hour's talk on its own, so we're just going to sort of graze that a little bit. Maybe if they invite me back next year, we can talk about that then. So there is going to be some assembly on the screen, as I've said, and before we go too far, I thought I'd just give a quick overview of the assembly structure so that we're all talking about the same kind of thing. There are two competing ways of showing Intel assembly. There's the AT&T format, and then there's the Intel format. I've picked the Intel one for these slides because it just makes more sense to me, having come from ARM processors way back when. And that is where the destination is on the left-hand side of the two things. So an instruction generally looks something a bit like op, where op is like load or add or subtract or exclusive or shift. Destination and source. And those destination and those sources can be one of three things. They can be a register, one of the RACs or RBX or RCX, as I've written here. There are 8 architectural registers that came from the 32-bit era. When AMD came up with the extensions from the 64-bit version of the processors, they added in another 8 registers, which they were much more sensibly named R8 through R15, rather than these strange esoteric names. There are also these multimedia instructions that have grown out of the revisions of the MMX instruction set from way back when. These are not general purpose registers. They are usually hold packed integers or packed floating point values, and they can be operated on in parallel for like multiplies and shifts and things, but they can't be used generally for like indexing, unlike the other registers. Also, you can talk about subsections of registers. So as I said, the 64-bit register RAX it has a 32-bit counterpart EAX and a 16-bit counterpart AX, and then AH and AL, which refer to the second from bottom and the bottom 8 bits respectively, all of which hark back to the legacy of the 8088 that still pervades even today's desktop and server machines. For the most part, the instruction stream of your original IBM AT will run happily unmolested, relatively unmolested, on an appropriate operating system on a modern Intel chip, which has a number of interesting side effects. The fact that we have this 30-plus year backward compatibility in the instruction stream. We'll get onto that a bit later on. So, as I said, it can be one of three things. It can be a register. It can be a memory operand. Anyone who's come from like the RISC world, as I did, will be absolutely staggered to realize that on the x86, a memory operand can be an absolute memory address, mem, plus a register, plus another register times 1, 2, 4, or 8. And that's a single operand. That's one kind of part of an instruction. It's a pretty complicated set of indexing. Or it can indeed be a constant. So those three things are register, memory, or constant. So I've got an example at the bottom here. This is one instruction. It's add d-word pointer array rbx plus 4 times rdx, comma ex. And what this really is read from array indexed by the b register plus 4 times the d register, add the A register to that value, and then write it back, all as one single instruction. That's pretty complicated, and that's where the C in CISC comes from. To sort of put this into context and to give us an example as we flow down the pipeline, I've got a very simple example here, which is a element-wise, give me the maximum value of each element. On the left-hand side, we've got the C code, and on the right-hand side, we've got one of the many potential compiled versions of that code. And I'm going to go through it instruction by instruction just so that we can kind of be on the same page about what's going on here. So we've got a 65,000 entry array. We go through each one individually. If y is greater than the x element, then we write the y element into the x element, and we're done. Obviously, there are much better ways of actually doing this in real-world code, but this is like a relatively simplistic example. So let's take the first instruction there. That's XOR EAX EAX. This is a very roundabout way of setting the EAX register to 0. We have, the compiler has decided that the EAX register is going to be where it's going to keep the loop counter. And why is it using XOR EAX EAX, you may ask? Well, it's pretty easy to prove to yourself that if you take any number and exclusive OR it with itself, you end up with 0. So why has the compiler done this? Well, the answer is the opcodes that translate into that XOR EAX EAX are 2 bytes long. To move the equivalent value with a constant value of 0 would require more bytes. So the compiler has picked a smaller representation of the same, functionally the same instruction in order to minimize the amount of code cache that's needed. You'll also notice, if you look a little bit further down, that later on it's using RAX, but it's XORing EAX. There are various different complicated rules about which parts of the registers get updated by which types of instructions. But when AMD came up with the 64-bit extensions for the Intel instruction set, they decided that if you were to write to the 32-bit register, you automatically clear the top 32 bits, which has a really convenient side effect here of us using a smaller encoding of XOR EAX EAX, which is just 2 bytes long, but clearing the whole 64 bits here. If it was XOR RAX, RAX, it would require a few more opcode bytes. So moving on to the next instruction, we have a read. This is one of those index reads. It's not quite as complicated as the one that has the multiply by 1, 2, 4, or 8 that we saw in the first slide. We're going to be reading here from RSI plus RAX. And by convention, the ABI is that RSI is the second parameter to this function, which corresponds to the pointer of the Y array. So we're going to read that out, calculating the address of this particular element by adding the element index to it, and read it into this XMM0 register. This is just reading one double precision number out. The next two instructions here are a comparison, which is comparing that value directly with the memory address of the x of I. So we haven't had to read the x of I value out in order to do the comparison. We can just have a compare which acts directly on memory. And if the value is below, we're jumping to label 2 here, which skips the next instruction. This is the equivalent of failing the if condition and moving on and not doing the update that's about to happen. This part then is the update, where assuming that y of I was greater than x of I, we're just writing out that value of xmem0 into the address of the of xi. And then we're skipping to the next element in the array. And you'll notice here the compiler has decided, rather than using that multiply by 1, multiply by 2, multiply by 4, multiply by 8 indexing trick, it's just multiplied the loop counter by 8 throughout. So it's adding 8 each time. We're counting in memory addresses instead of actual I values. And commensurately, we're going to be comparing the end of the array here with 8 times the 65,000 that go in there. And then if we haven't reached the end of it, we go back to the beginning. Otherwise, we're done. So hopefully that's got us on the same page when it comes to assembly. So the Intel pipeline is a very long and complicated beast. And I'm going to talk about groups of the things that go on down the pipeline. But first of all, what is a pipeline? I think probably most of us know that modern processors are pipelined. Why? Well, it's probably never been the case that an instruction could complete in a single cycle, even back in the old days of much simpler instructions, much slower clock speeds. And so there has always been a partition of work. And in the original processors, the original 8-bit processors, certainly that I worked with, the 6502 and the Z80, each instruction would take 5 or more cycles to complete. And the instruction would be fetch the byte that encodes the opcode, fetch the operands, do the process, write the results back. And then we'd move on to the next instruction. So it would be taking 4 or 5 cycles each go. Then people realized that while we were decoding one instruction, we could be fetching the next one. And while we're executing the instruction, we could be decoding the previous one and fetching the next one again. So by pipelining, we can increase the throughput in a production line style, which is great. So now, every clock tick, a new instruction comes into the front of the pipeline, and one instruction leaves the end of the pipeline and is completed. So every clock tick, something useful happens. We haven't changed how long it takes to execute a single instruction. It's still 4 or 5 cycles, but every tick, we're getting one more thing out. And that's very much the approach that a production line takes when you look at like car building. If you were here for Jez's talk yesterday, and he was showing up all of the sort of pipelining stuff and the work that Toyota have done in order to optimize their pipeline forward, it made me think of this as well. But the problem is that when you're making cars, one car is not dependent on a previous car that was made, which is not true for instructions. The instruction stream necessarily has inter-instruction dependencies. If you're doing a multiply, and the multiply takes 5 or 6 cycles, then you want to use the result of that multiply in the next instruction. Well, if you're pipeline, you're kind of out of luck until the multiply is completed, and then you can start the next instruction. So what would typically happen is the pipeline would stall at that point, and the next instruction that needed the result of the multiply would have to wait until the multiply had finished, which kind of is a shame. We're using up our pipeline bandwidth there, or losing bandwidth. More problematically is the fact that our stream of instructions coming in is not a linear stream. Within that stream are branches, which may be conditional. And so anytime the code jumps around and starts needing execution from a different part of the program, we basically have to start again. We get to the point where the branch happens. If the branch is taken, we're like, well, okay, unfortunately, all the work that's coming down the production line is wrong. We need to start again. And so it comes back to the beginning. We start from the beginning of the production line, but at the new address. So what can we do about that? Well, we can make a guess. That's the simplest thing. How about if somehow we could look into the future and decide, well, what is it really that we're doing? What actually is the sequence of instructions that are coming down? It's not just address 1 followed by address 2 or followed by address 3. Let's have some kind of prediction logic. Well, we need a crystal ball to work out that, really. There is no good answer for this, but there are some really good heuristics, which is exactly what the branch predictor has. So the branch predictor, this happens right at the beginning of the pipeline. Whoops. Before we've even fetched a byte of RAM, we are guessing where that byte of RAM needs to come from. We need to predict if it's a branch, if there's a branch coming up, where it goes. And if it's a conditional branch, we need to work out, well, is it going to be taken this time or not? So we have a little cache, and that cache is called the branch target buffer. And in that cache, we store every branch instruction that we've seen recently. We store where that branch instruction goes. And in the case of conditional branches, we keep some kind of state that tells us, gives us some prediction about whether or not that branch will be taken the next time we see it. The simplest state we could keep is literally, have we taken it again recently? So one way that's done is with a 2-bit saturating counter. We just say every time we take a branch, we move one stage to the right here. Every time we don't take a branch, we move one stage to the left. And then if we're in the green patch here of weakly taken or strongly taken, we say, well, let's assume we're taking it again. And if we're in the red patch, we just say, no, let's carry on. Let's ignore this branch. Let's just keep on streaming from memory in memory order. This is great. This is a really simple thing to do. But it's not very accurate. If you think about what branch patterns really look like, you've got loops, where you're going to go over the same piece of code multiple times, in which case this probably could work quite well. You know, every time you reach the bottom of a loop, there's a branch to back to the top, and if you've got like 100 iterations of a loop, then it's going to be right most of the time, and then you're going to mispredict at the end. Maybe that's fine. But if you've got any other more complicated inter-branch dependencies, then you're basically out of luck. This stuff is not good enough. We need to take into account sort of the history of what this branch has done before. Maybe we need to look at what other branches are doing in the system and try and add them into the mix and see if we can't guess based on that kind of fingerprint of what the program is up to. So one thing we can do is keep track of what happens given the history of a particular branch. So for each branch in that BTB, that little cache, we're going to keep, in this instance I've put 4 just because it's easy, 4 bits of what happened the last 4 times we saw this branch. And then we're going to use that to index into a table of, given the fact that we've seen 2 branches taken and then 2 branches not taken in this sequence, that gives us an index 3. We go over and look in the history table. What happened the last time we saw this pattern of branches being taken? Oh, we took a branch. Let's predict that we did that. And then obviously as we come round and the execution unit actually makes the decision about whether we took the branch or we didn't take the branch, we update our table, and over time we learn, given this pattern, this is what happens. That's cool, but there's a problem. That's only 4 bits of history. That's the 4 times we've previously seen this branch. That's not much state. Programs are much more complicated than that. It doesn't scale at all. The table of counters you saw on the right-hand side in the previous slide is 2 bits per entry, but it goes up with 2 to the n. So if we add 8 bits, if we want to do 8 bits of history and take into account the previous 8 branches of this, 8 instances of seeing this previous branch, then we need 256 lots of 2 bits. And that just, given that we want to have a cache of many, many branches, that's just not going to scale very well. There is some circuitry in certainly some of the older Intel processors that have a separate sort of guess about for loop behavior, where they keep track of the number of times a branch is encountered and taken every single time except one, which kind of covers the case of having something which goes through like 50 times and then doesn't get taken, and 50 times doesn't get taken, 50 times doesn't get taken. Well, that's probably a loop of 50 that we're going to see time and time again. But it's difficult to determine whether or not something is really a loop or whether or not it's just a condition that's often true. So there's only limited mileage in taking that kind of approach. What Intel have done in their most recent generation of hardware is to take a global view of the branch prediction problem. They take 32 bits of global history. That is not any particular branch's pattern history, but any branch, any conditional branch we've seen recently, the 32 most recent branches, what were we doing in those cases? And instead of having 4 gigabytes worth of branch prediction table for those 32 bits, we hash that into a smaller but shared pattern table. So we can have quite a big table of these patterns, but we have to accept that there are going to be collisions. We still use a per branch table for the destination of any one particular branch. What does that look like? It looks something like this. So now we've got 32 bits of what on earth have we done recently in terms of branching. We take that, we take the branch address of this particular branch we're trying to predict, we smoosh them together with this hash here, and then we go into this table where, given this kind of program state, this is what we did before. And this is really cool, except that this global history table has no idea whether or not it's really this branch that we're looking at. Any 2 branches that hash the same element, we just use whatever's in their branch table, their history table, excuse me. And that means that you can get into situations where branches fight over the same slot in the buffer, and we mispredict a lot of the time. And there are ways around that which, as far as I can tell, aren't actually happening on modern Intel chips. But certainly other architectures then also have like another predictor, a sort of a meta predictor per branch, which just says, how often did I predict this branch correctly? And every time we're right, we move one to the right, and we say, OK, we'll do what the branch table thing says. And every time we get it wrong, we move it to the left, and then we say, well, do the opposite of what the branch table thing does. So if you have two branches that have opposite behavior that land in the same slot, at least we can handle that situation. But as I say, there's no strong indication that Intel are doing this. They say that they aren't. Also, we don't know how big this history table is on the Sandy Bridges, so your guess is as good as ours, really. But assuming that these are only 2-bit each, I'm guessing they use quite a few bits of history. But first of all, does this actually matter? Before we go too far down this thing, I realize we haven't even got into the first stage of the pipeline proper yet. We're just still trying to work out where the heck we're going to get the instructions from. Is it important? Well, here is a bit of Python code. Python obviously is an interpreted language and is full of internal branches inside its own interpreter. And so it would be interesting to see whether or not we can even see the results of the branch predictor at this level. And so this example is going to run over an array, and it's going to sum up the total of the array. And it's also going to count the number of elements that were below some threshold, 128 in this case. And it's going to sum up those guys. And then at the end, we return like the average of the entire array and the average of the ones that were below 128. If you feed in a big old array of values into this, each between 0 and 256, this is what happens. If that set of values is completely random between 0 and 256, sorry, it takes 102 nanoseconds per element. But if you sort that same input value, so same input set before you pass it into the algorithm, it only takes 94 nanoseconds an element. Excuse me. I think I should drink some of this. 94 nanoseconds an element. That's a speed up of 8%. That's not bad. Now, how can I be sure that it's branch prediction that's helping here? Well, why would branch prediction help here, I should say first? Well, in the sorted case, of course, the first half of the array, this if statement will be true. We'll always go into the num clipped and the clip total plus equals 1. So somewhere, one of the many branches inside the interpreter will always be not taken, as it doesn't skip over the if statement. So then we run through the first half of the array, and we hit the first value that's 128. And at that point, the prediction is wrong. Hopefully, though, within the next two or three iterations, we will have learned that actually this is now the new world order is that we're going to be taking this branch every time. And we then predict correctly from then onwards. So it seems like branch prediction, getting the branch prediction right here, would be useful. Whereas in the random case, of course, the branch predictor is going to be trying to infer a pattern for this if statement, where in fact no pattern exists at all. There are a variety of tools that you can run, and I ran one called perf, which I thoroughly recommend for this kind of investigation. And if you run with and without the sorted data, you can see that the same number of instructions are taken, the same number of CPU retired instructions go through the system, the same number of branches are encountered, but the branch prediction rate is vastly different between the two. So it's not any other artifact as far as I can tell, although it is still surprising to me that in an interpreted language it still can matter. What you can do about this, I don't know, in a practical sense for this particular toy example anyway. Okay, so I've made a reasonable case for why a branch predictor is worthwhile. What happens once we've predicted where the program flow is going? Well, the results of the branch predictor are a stream of instruction addresses. This is like where we want to be fetching from. And that moves on to the first stage, which is this fetching and pre-decoding stage. The fetcher is responsible for reading the instruction stream. It's responsible for doing the TLB lookups, the virtual to physical address translation, and for streaming in blocks of instructions. The instructions look something like this. The fetcher reads them in 16-byte chunks. And it has an interesting thing to do, first up. So later on down the pipeline, we want to unlock as much parallelism as possible. And that means that we want to do actually more than one instruction at a time, if that's at all feasible. But because of the long and tortured history of the x86 architecture, we're kind of left with this strange format of opcodes, which no rational being would come up with. So if you look at like RISC instructions nowadays, they're usually fixed size. It's very easy to see where each instruction is. But in an Intel sequence, there's no obvious way at all to determine where the bytes are, where the instructions are inside that byte stream. This is what the fetcher does. It fetches it and it looks out for the beginning of each instruction, which is an amazing achievement. If you think about it, in 1 or 2 clock cycles, it has somehow scanned this list of instructions, decoded where the beginning of each instruction may be, and somehow done that in parallel. Because necessarily the beginning of one instruction follows on from the end of the previous instruction, there's a dependency from each one carried along. So the only way I can think they're doing is somehow like parallel decoding all 16 possible places in the instruction stream where instructions may be, and then somehow filtering out the ones that don't make sense. But whatever it is, it's an amazing achievement. And so this instruction stream here, this sequence of bytes, is actually the first few instructions of the example I showed you earlier. There's that 2-byte XOR EAX. And you can see we've pulled out 4 instructions here. And then we've got the F2OF, which I haven't put down here. It's like the beginning of the next instruction in the stream, which will sort of be prepended to the beginning of the next fetch in the next cycle. I was going to say something else there, and I've forgotten. Sorry. OK, so we've got our 4. Oh, yeah, sorry. At that point here, the pre-decoder doesn't know what these instructions are. It only knows where they lie in the sequence of bytes. That's all they can do, and they're given the amount of time that they have to do this. But those bytes then flow on as a sequence of bytes and offsets where the instructions may start in the stream onto the decoding stage, which is where finally the Intel engineers have sort of admitted defeat of this really complicated Byzantine instruction sequence and have decided that they want something more pure inside. So at this point, the CISC instructions that come through are converted into a sort of internal RISC. Now, Intel don't publish Intel don't publish the format of this internal RISC. There is some sort of literature about where the execution units use the various types of microoperations. So microoperations is what they call this RISC set. And within those microoperations, the more complicated instructions, like the read, modify, write instruction I had on the first slide, the load from a complicated memory address, add to it, and store it back, actually devolve into the 3 instructions that any normal person would have written in a RISC world. That's a really important thing to do, because later on down the line, we're going to be able to break those parts of the instruction up and schedule them differently, so that if parts of the chip are busy, like if the multiplier is busy, we can still do the load part of a load instruction, which has a multiply component to it. We can potentially have a, yes, sorry, that's probably a good enough example, sorry. So breaking the instruction into pieces does help, because we can schedule the individual parts around, and we have a lot more fidelity later on for parallelizing things that wouldn't otherwise be parallelized if we just naively kept them as atomic instructions that we wrote to start with. The decoders here can handle up to 4 instructions in a single cycle, which is impressive. So those 4 instructions I showed you in the previous slide will come through into the decode stage, and they will be turned into microoperations in one cycle. There's some complexity to do with the different decoders. The first decoder, for example, is capable of decoding absolutely any kind of instruction and generating any number of microoperations, whereas the other 3 decoders that there are that are in parallel can only do the simpler instructions. So there is some kind of mileage into very carefully scheduling your instructions into a particular pattern to allow them to flow through as fast as possible. On the newer processors, that's less important because of the micro-op cache, which I'll talk about in a second. But you'll see if you ever go into the deep depths of like GCC's internal instruction scheduler, it tries its best to move things around to fit this kind of pattern. And indeed, actually, as a sort of a side note, if you open, one of the better places to sort of see the documentation for this, for the reverse engineering of what goes on inside, is to look inside the bowels of the compiler, as there are some automata inside the compiler that try to predict what the processor does internally and schedule instructions to fit in with the predicted flow. So we have these 4 decoders, and they output these microoperations. 2 other things take part at this point. We have microfusion, which is the name for taking 2 microoperations and kind of treating them as one. Although we've carefully devolved them into different pieces, that takes up a lot of bandwidth. If you imagine we've got like a stream of instructions coming in, we're kind of expanding out the number of operations. So we've got a sort of fan out thing going on, and that obviously consumes resources on the chip. So for the very common operations like stores, which require an address calculation as well as the actual store, well, they don't need any more temporary space. There are two separate pieces of work. One is to calculate the address and one of them is to do the store. But wouldn't it be nice just to sort of treat them as one atomic unit as they flow down the pipeline, but just schedule those two bits differently? So that's what microfusion is. It's taking two micro-ops and kind of bundling them together as a sort of tuple of things to do together. And then we've got, more importantly, macrofusion, which is where the converse happens. Rather than multiple micro-operations being generated from a single input instruction, we take two input instructions and we can generate only one micro-operation. An example of this is the compare followed by a branch. It's so common that we would want to like compare our loop counter with some value and then branch if not equal, or decrement a value and then branch if it's not zero. Those kind of things, which most instruction sets actually have a decrement and jump if not zero kind of feel to them. x86 doesn't, but at this point, if you have two instructions one after another that have this pattern, it will be turned into a single micro-operation. So we kind of claw back a little bit of this fan out that we were getting from further down. In the Sandy Bridge and above, there is something called a micro-operation cache at this point too. So the clock has already ticked like 6 or 7 times to get to this point, and so an awful lot of valuable work has been done. It would be useful to hang on to that intermediate results, especially if, as oftentimes, we're going to be revisiting this code in short order. So the micro-operation cache stores the results of the decoded operations at this point. There are about 1,500 entries, and it's a very complicated sort of cache that doesn't map to a normal like memory cache in the way that you would probably think. But if you just think of it as something which can hold a smallish loop in, it's useful well, the reason that this is useful is that when we do a branch later on, if we discover that we've been going the wrong way down the pipeline, but the destination of that branch is inside the micro-op cache, we don't have to go all the way to the front of the pipeline. We can sort of short circuit and start at the micro-op cache, and only from then onwards do we need to start reprocessing instructions, which reduces the latency of a mispredicted branch. So although we've invested all this time earlier trying to work out which way the branch is going, if we get it wrong, the micro-operation cache can save us a bit of time recovering from that. As I've said, Intel don't give an awful lot of examples of what their micro-operation format looks like, so I've kind of, on the left-hand side here, given an example of the code again, and on the right-hand side, I've invented my own sort of format for what these micro-operations might look like. And the convention I've got here is that one line of text is one micro-operation. So the things I want to sort of point out in this stream are that compare instruction, which compares with memory, is two micro-operations. There's a sort of temporary value, an unnamed temporary, that's read out, and then the comparison happens as a separate micro-operation. And then there at the bottom of the loop, what we've lost in that one extra micro-operation, we kind of claw back here because the compare followed by the jump maps to a single micro-operation, which is the macrofusion. But even this isn't really what happens. So at this point, this mental model that we might have of putting the code side by side is not what the processor is seeing at this point, because what the processor is really seeing, of course, is a sequence of instructions flowing linearly down in predicted program order. The branch predictor's done its magic. We have the fetcher has just fetched whatever it's been told to fetch, and this is what's flowing down. So I've kind of tried to capture this on this slide here, where on the the left-hand side, I've kind of put the address to give you some idea and to sort of highlight what I mean here. Take this comparison here. This is one of the comparisons around the if x is greater than y. And in this instance, I've just arbitrarily decided that the branch predictor has predicted that this particular one is going to be taken. So rather than the next instruction being the NOD x14, which would be the next address of the instruction, I've said, hey, we think this one's going to go to 19. Go to 19 now. And so that's the next thing that's going to be in the pipeline. Similarly here, this is the loop at the bottom where we've done the compare and if not equal. And obviously for the vast majority of cases, that's going to be taken, as for everyone except one iteration, that is going to be the case. So we hope that the predictor has guessed that. So again, the next instruction will be back at the top of the loop. And then down here, just for comparison, this one has been predicted not taken. So rather than being the hex 19 address of the next of the GOTO, it's the next address linearly in memory at hex 14. Now, of course, this sort of underlines what happens when the branch actually gets to be executed, and that is the branch unit has to say, well, which way did it really go, and was I right? And if I'm not right, what do I do? Well, we've already said about this, we're going to be flushing the pipeline, but how does that happen? We'll talk about that in a second. Okay, so we've decoded our stream of instructions. We're about 6, 7, 8 clock cycles, depending on your model, down the pipeline, and we hit this thing called the renamer. The renamer sort of takes another RISC view and somehow morphs the x86 instruction set to fit that. So the x86 only has these 8 or 16 in 64-bit mode registers that we can talk about, ignoring the XMM registers for now. But if you look at any RISC chip, there are hundreds, if not thousands, of available registers. Why is that? Well, if you want to separate out independent instruction flows and have parallelism, inter-instruction parallelism, you need to be not stomping on your registers at the same time. If you use the same register twice, well, you have to wait for the previous usage to finish before you can reuse it to do something else. It used to be the case that registers took up lots of the real estate. If you look at like old circuit diagrams, or rather old dies of like the 6502, for example. There's a great project where people have been taking the top of 6502s and scanning them with high-resolution cameras and then like literally backing out where every single transistor is, but they can draw sort of diagrams of where everything is. You can see that the registers are actually a substantial blob of the die. That's no longer the case. Compared to like the caches that are on there and all of the complicated logic, the registers are a tiny proportion. So having only being able to encode 16 in the format, even with all the extensions that are in there, is kind of a limitation for this. So the renamer does on-the-fly dependency analysis and turns your code into single static assignment form, and then makes up intermediate temporary values and maps them into a sort of a suite of 100 or more instructions. 100 or more registers. So we are no longer beholden to the 16 registers that came in. We can use these intermediate values throughout. And these intermediate, let me give you an example. That's probably the best thing to do here. So here on the left-hand side, I've got a slightly different example. We've got a routine which takes 2 values and increments 2 different globals. And quite reasonably, here is a piece of code that the compiler could have output, which is read the global A into EAX, add EAX to the first parameter and store it out, and then the same again for B. Notice it's using EAX again twice. Pretty sensible. But if that read takes a long time, and I think we all know that accessing memory usually is pretty slow, then, well, it's clear and obvious that these 2 instructions after it, which depend on the value, can't run. That's fine. But we've used EAX in the next block of code. What happens if global B is in the cache already? What happens if we'd have used a different register here? Maybe this could have been scheduled. But we've used EAX. We can't do it. It's going to be stomped over by whatever this instruction stream is doing. So the renamer takes a look at this, puts it into SSA form, and comes up with something which looks a little bit like this. Again, there's no kind of documented format for this, so I've kind of used a suffix on each register to sort of indicate the new name that each register has. So rather than EAX on the left-hand side, we've got EAX sub 1. And then we add EAX1 to EDI1, and we write the result to a new temporary intermediate register called EDI2. And that's the thing that we write back out again. And then critically, down in this second blob, we have determined that this value of EAX is completely independent of the previous value of EAX. We might as well have used another register. We could have done. We just couldn't have encoded it, or the ABI forced us to use a particular named architectural register. But at this level, inside the chip, we can make a new one. We can just say, hey, let's call this EAX sub 2. And now, those 2 pieces of code are independent of each other and can run together in parallel, or one can go in front of the other. And we unlock parallelism, which otherwise would have been prevented. The way that this is achieved is that the renamer keeps track of which of these intermediate temporary registers contains the current version of any of the named architectural registers. This is the register alias table. And it maps into either a reorder buffer, which is like a temporary scratch space of all of these micro operations that have yet to be executed or have executed but haven't finished completed yet. Or it maps into the permanent register file, which is like the canonical place where the real EAX and the real EDX live. Interestingly, right up until the Sandy Bridge, all of this complicated sort of internal logic where all these various things are being shuffled around and predicted and whatever was not the bottleneck. The actual bottleneck was this PRF read here. So if you've modified a register recently, it's going to be living in one of these temporary variables that are inside this 100+ array of intermediate results. But if you haven't modified a register recently, it's in the real register file, over in the permanent register file. And at this stage, as we leave the renamer, any instruction that needs like the real EAX and the real EAX isn't in the reorder buffer already, we have to read from the permanent register file and put it in there. But there were only 3 read ports on the register file, which means that anytime you needed more than 3 registers that hadn't been modified recently, you would take multiple clock cycles to read them. And now, that sounds like a lot, 3 registers every single clock cycle, except that by now we've devolved our instructions into a stream of micro-ops. Each micro-op has up to 3 operands, and we're trying to do 4 of them at once. So we can easily contrive 12, and that means we're going to take 4 clock ticks just to move into the next stage. So thankfully, on Sandy Bridge and above, they've fixed this, and you will no longer see this as being a problem, assuming you guys are on Sandy Bridges, of course. The other thing that a renamer is smart enough to do is understand these funny little things like this XOR, EAX, EAX we did earlier. So naively, if you were just tracking like the value of each, or rather whether or not a register was dependent on a previous incarnation of that register, this XOR, EAX, EAX looks like it's dependent on the previous value of EAX, and it's not. The renamer is smart enough to know that this means give me a new EAX, put the value 0 in it, and move on with your life. And in fact, in the newer chips like the Ivy Bridge and newer, at that point, the micro-operation actually falls out of the pipeline. We don't need to do any more work. The work is done just by allocating a new empty slot that has a 0 value in it. For some of the instructions as well, the ones that like compare not with yourself, which for the XMM register sets it all to 1s, that also can happen on the Ivy Bridges at this point. And inter-register moves, so oftentimes, again, to fit the ABI, we'll be moving values between registers just to make sure that things are in the ESI or the EDI register ready to call a subroutine. Well, all that is just an accounting update. If we think that the most recent value of EDI is in slot 7, well, that's all we need to record. Okay, it's in slot 7 now. And again, the move itself doesn't have to happen. So a lot of the instructions can be peeled out. A lot of the sort of like in-between instructions, the moves and the shifts, the moves and the exclusive orders with itself can actually disappear out of the instruction stream at this point, and we just update our tables. So the reorder buffer is this temporary scratch space of these 100-odd in-process micro-ops and their operands. The reorder buffer holds the state. It knows what the micro-operation is. It knows the inputs. And in the case of micro-operations that don't have their values ready, it knows which other operations it's waiting on. And it snoops the results of completing instructions. So as a dependent instruction completes, it's broadcast across like an internal bus, and any micro-operation that's waiting for those results can now read it in, store it, and become ready to run. This is also the stage where that permanent register read happens. And at this point, the micro-operations remain in the buffer until the very last stage of the pipeline. Okay, we're nearly at the point now where we're going to get into the magic territory of actually executing these instructions, and for the first time, we're going to go out of order. The reservation stations is like the last step. This is where some kind of scheduling algorithm, which again is very, very vaguely described in the literature, is responsible for working out which of the micro-operations are going to go to which parts of the chip to actually be executed. There are 6 execution ports, and each execution port can only do a subset of instructions. There's a lot of overlap between them, but there are also like unique areas that can only do one particular kind of instruction. And that looks, oh, we're here. Yes, so we've actually going to talk about which parts do what now. We've just done the top part here, which is the in order part of the queue, and now we're into this scheduling domain down here, and it's worth talking about these ports here. So we've got the 6 ports here. This is Sandy Bridge, there's 6 ports. The first 3 ports on here, which are oxymoronically 0, 1, and 5, they all have an ALU attached to them. So they can all do the simple operations of move, if they haven't already been renamed out of existence. They can do shifts, they can do ORs, they can do exclusive ORs, they can do comparisons. And what this means is that in any one tick, if there are 3 simple operations ready, they can all start executing. That means that we're now starting to do 3 things at once. That's great. If you're doing loads or stores, you're going to be using these ports over here, ports 2, 3, and 4. We've got 2 load ports and 1 store port. So you can see that there's sort of a bit of contention there in terms of the number of these things going on. There's an extra thing about the stores. As I've said, the indexing modes are really complicated. We can have like this base address plus 2 registers with one of them being multiplied by a constant value, power 2 constant. For reasons I don't fully understand, at least on Sandy Bridge, this 4th port, the store port, doesn't have the logic, the circuitry to do that address calculation. And so whenever you do a store, it's not just the case that you have 2 loaders and 1 store, so there's a disparity between them. Every time you do a store, it has to borrow one of the load units just to do the address calculation. And that's an example of those fused micro-operations where a store is both the address calculation and the load, but it kind of borrows 2 ports at once, even though it's only 1 actual slot in the reorder buffer. Other things to note here is that once we get into the more complicated instructions, like floating point multiplies and adds, various shuffles, there are only 1 or maybe 2 units that can do that work, which limits the amount of those we can do at once. Yes, 6 units. Yes. We have 6 units. They're mostly pipelined themselves, so that means that each unit, say a multiply unit, may take 6 units, 6 clock cycles to complete, but we can start a new multiply every single cycle. So although the individual results of one multiply aren't ready until the 6th tick, we can start a new one each clock cycle. This means that the issue rates down here are up to 3 of cycle. That's what I was saying with those ALUs. With the fact that we have 3 ALU units means that every single clock, we can start 3 of those guys. We can only start 1 floating point multiply every clock cycle, which is a shame. In this instance, I'm also only talking about like the scalar multiplies that can happen. If you're starting to use the XMM instructions to do like multiple floating points in parallel, where you like have 4 or more packed into the XMM registers, only one of those can start each go, but they're like 4 independent multiplies, or 8 depending on the width of your registers. There's another sort of component, as well as the throughput issue of like how many we can start each tick. We have the dependency between instructions. So for logic ops and moves, if you start a move or an exclusive OR, the results are ready on the next tick. So the next instruction that depends upon that can start the very next cycle. For integer multipliers, that's 3. For floating point multipliers, as I said, that's sort of 5-ish, 6. For square roots, 10, 24. For divide and remainder, we're looking anywhere between 24 and 84. It depends on the actual data you're using. And the really key thing about this is that is not pipelined. We can only have 1 integer divide going on at once. So in stark contrast to those multiplies that are going on, where we can have 1 at a time, but one every single cycle, a divide or a remainder is going to take 80 cycles to get the result out, and we can't be doing any other divides or remainders. So all of your hash tables that you've written, where you're using like the modulus with a prime number size of table, maybe you should consider looking at using a more complicated hashing function, which uses multiplies, exclusive ORs, moves, shifts, which can all be computed a lot quicker, and then just ANDing with like a power of 2 to fit into a power 2 size table, rather than waiting for 80 cycles for your divide. Having a higher quality hash function might be a better trade-off. Anyway, I am starting to run out of time. This is my quick dib into the excuse for why I can't have 4 gigabytes of cache RAM. Why does it take 3 to 250 cycles to access RAM? On the left-hand side here, I have 1 bit of static RAM. That's such as you'd find in your cache. On the right-hand side, I have 1 bit of DRAM. Now, it's pretty clear that the left-hand side is much more complicated than the right-hand side, but why is that bad? Well, on the left-hand side, we have a pure logic device. This is a discrete component. We're going to get 0 or 1 out of this at all times, but it requires constant power. It requires 6 transistors and a bunch of complicated overlapping wires, which make it very, very difficult to lay this out in a high-density way on a chip. I don't know how Intel do it, but you look on the die and there's these beautiful areas which are clearly the cache of the same thing over and over again. But somehow they've been able to get that done. But it's power hungry. It means it heats up. It's a problem for heat dissipation. But it's a logic device, which is great. On the right-hand side, we have something which is an analog component. This capacitor down here stores some very small number of electrons to store whether there's a 0 or 1 there, which means we don't need to pay powering it when we're not accessing it. We can turn the power off and it'll be there, except that it drains away over time, so we have to keep occasionally topping it up, which reduces our memory bandwidth. We just have to keep using that just to keep topping it up. But more importantly, every time we read from this, it's an analog to digital conversion, which takes time. So why would we even do this? Well, obviously, we don't need power all the time. That's great. These are very, very much simpler. We can lay out these out at much higher density, which is why your DRAM cells are much, much, much more tightly packed, and you can have your gigabytes of RAM. And obviously, the other part to this is that the DRAM is usually physically separated from the chip rather than being on die. As such, there's propagation delays. It just takes a while. Unfortunately, the laws of physics are against us. Electrons don't move anywhere near the speed of light, and they've got to move quite a long way from the RAM chip to get onto the processor. So that's kind of my apology for why we can't have lots of cache RAM. There's some example timings here, and I think we all know that it's better to keep things in the level caches, the lower level caches. We will blast through this last couple of bits here. So the last thing that happens is when the instruction has completed, it broadcasts its result, which frees up any of the micro operations that are waiting to be scheduled. They become ready to run if they are, in which case the scheduler will pick them up the next tick. We've got some complicated things to do with store forwarding, which I haven't got time to talk about now. And the last stage is this retirement stage, which is where some of the better magic happens. So in the retirement stage, so far, we have kind of each instruction that's been flowing down the pipeline has been a transaction that has yet to commit. Although we may have read from memory, any writes that we've done are sort of holed up in a storing buffer that hasn't yet made it out. Why is this important? Well, we reordered everything along the way. What happens if we got one of the branches wrong? But what happens if it took us a while to find that out? We'd already started doing some of the work that was the other side of that branch. We need to undo that work. And the way that that's done is by just not committing the instruction, basically blowing away that transaction that the instruction started and not writing back to the permanent register file, not allowing the store to actually flow out to the outside of the chip by not allowing the instruction to retire. Similarly, exceptions like divide by zeros, and it may be the case that a divide, the values for a divide weren't known up front, and so instructions beyond the divide have already finished and completed, but the divide by 0 has to happen with the old value of those operands. And there's kind of, this is starting to become exposed to the programming model, this whole idea of having these sort of transactional instructions where, so for example, Haswell has this software transactional memory model where you can ask to be notified if various parts of RAM are accessed while you're running, and abort a set of instructions so that an atomic operation from your point of view doesn't require a lock. It just means the transaction being rolled back. I've since discovered that this is not actually done by effectively the same logic as the branch prediction. It's probably done in the cache level, but there is talk in the Skylake, which is like 2 more revisions up, of them exposing this instruction level transaction to us as programmers. Okay. We've reached the end. There's an awful lot of stuff that's going on under the hood, and I don't think I have time for questions, judging from the time, but thank you very much for your time, everyone. There's some example resources up there. Thank you.